Hello, this is Ms. Hobbs with Washington High School Physics, and we are going to be talking about series circuits in this presentation. So series and its counteract parallel are pretty important concepts when we talk about how we actually light our houses. And we'll also maybe talk about the difference between electrical power, alternating current, and direct current. I think we'll probably split it up so that series is one video and parallel is another, with electrical at the end. Okay, so with a series circuit, everything is in series. And in the lab that you're going to do, you're going to be setting up a couple of bulbs, and they're going to be in a direct line between each other. And we're going to explore what the impacts are of putting those bulbs in a direct line. Okay? And we'll refresh our understanding of Ohm's law because we'll have some relationships that deal with voltage, current, and resistance. And we have talked about electrical systems before and alternating current and direct current. We've talked about Thomas Edison, and we will talk about it. It really wasn't Westinghouse that developed alternating current. It was actually Nikola Tesla, and we'll go through a short presentation on why Tesla was freaking awesome later. But you do need to know the difference between alternating and direct current. That's why there is a squiggle line for the direct current and then a line with a couple of dashes for the alternating current. So when in doubt, just use the alternating current form. So we've got a series circuit. They are in a direct line with each other. The current goes through this one and then has to go through the other one. So all through the same points in the circuit. Stuff that you buy from Dollar General usually doesn't work. I always have that problem too, where I have bulbs for Christmas lights and I have 50 bulbs, and they all have a input where the current goes in, filament gets excited, heats up a little bit, current goes out, current goes in, filament gets excited, heats up a little bit, current goes out, etc., etc., etc. However, if you remove one bulb, so one bulb breaks, doesn't work, whole string will go out because now it's a complete open circuit. So if you know the resistance of each device, you can find the total resistance of the circuit by adding up the resistance. So this is kind of a duh moment. They're all in a series, so they all add together. So you can see the resistance of the ohms right there. And then the total resistance is 1 ohm, 1 ohm, 1 ohm for a total of 3 ohms. Now this will get a little bit more complicated when we compare and contrast with parallel circuits. But that's what the individual resistances are. And we need to know that because we need to know how much current we need to flow through it, how much voltage we need to flow through it in order for all the light bulbs to light with an appropriate amount of brightness. So this is the water analogy that we've been talking about. And adding resistance is like adding pinches to the water hose. It becomes more and more difficult for the total amount of water to pass through. Okay. Now, keep in mind, everything has some resistance, even thin wires. And one of the things that material scientists are working with is creating current in circuits that have no resistance. We know that the resistance decreases as we lower the temperatures. So things that have a really cold temperature, like very close to absolute zero, have very little resistance. And so what's one of the things that we're looking about to increase our networks is seeing what we can do to create similar conditions to that without actually having to deal with the cold temperatures. All right, so devices in a circuit convert electrical energy into other forms of energy. We've talked about potential, mechanical, chemical, that kind of thing. And power is the rate of the energy transfer, and that's also measured in watts. So the current itself doesn't go away. The current always returns back to the batteries, but the power is what can be decreased. So some of the power goes to the first bulb, some of the power goes to the second bulb, some of the power goes to the third bulb. If you don't have enough current to carry the power all the way through, then you don't have enough to light up any of the bulbs. So what is happening here with that power that's decreasing is called a voltage jump. As the device in series uses the power carried by the current is reduced. So a little bit of energy from electrical energy is transformed into thermal energy and light energy. And that light energy goes away, it goes out of the system, and it can't come back in. So this guy is working with a little bit less energy available. There's still current flowing through, but there's a little bit less energy available. And so this bulb is going to be brighter if it's just with 1 than if it's with 2. And then also with 3. And each one of these has got a voltage drop. So when you do the lab, you're going to be connecting the power points there, or the prongs there. So we use this for Ohm's law as well, because it'll allow us to tell us what the relationships we need to have, what the variables we need in order for things to work. In the circuit, each bulb has a resistance of 1 ohm. So each voltage drop of 1 volt, so remember that's electrical potential energy, when 1 amp throws to the current circuit. So if we increase the amps, we might be able to change a few things, right? That goes back to the Ohm's law thing. I'll continue. So you got the voltage drop diagram here. And then we got Kirchhoff's voltage law. He's going to show up again in the parallel circuits as well. And it shows it through. And we'll be on parallel circuits next, but that will be time for another video. Thanks. Bye.